Today we are jumping into a topic that I think a lot of people, they feel like they know it, but then you peel back the layers.
It's one of those things that's deceptively simple on the surface.
It really is. We're talking about energy.
Or more specifically, energy abundance. And the incredibly intricate machinery your body uses to manage that abundance.
Exactly. The body's whole energy management system. And usually when people hear that, their brain immediately goes to blood sugar.
Right.
They think about that sugar crash after lunch, or maybe they think about diabetes. And look, those are huge parts of the story. And it's this really dense, fascinating physiological breakdown of the pancreas and insulin and glucagon. It paints a much, much bigger picture.
It really does. Because if you just focus on sugar or glucose, you kind of miss the elegance of the whole machine. This isn't just about keeping your glucose levels flat. That's not the goal. The goal is to manage a biological switch.
A switch.
Yeah, a mechanism that has evolved over millions of years to handle two very, very different states of being. You have times of feast and times of famine, or, in the language we'll use today, abundance and scarcity.
And the stakes for getting that switch right are incredibly high. I mean, reading through this, you realize that if this system goes offline, even for a short time, the body just completely unravels.
Oh, it's catastrophic.
It's not just about feeling tired, it's chemical chaos.
Total chaos. We all take it for granted because it works so silently, in the background. But the precision that is required to keep your fuel levels stable while you switch from eating a massive meal to, say, fasting while you sleep, it's just engineering at its absolute finest.
So we have a huge stack of notes here. We're going to cover the anatomy of the pancreas, the chemistry of these hormones, how they talk to our cells, and then ultimately what happens when it all breaks down in something like diabetes. But I want to start with that concept you just mentioned, the switch.
Right. So at the highest possible level, your body is constantly making a decision. It's asking, am I storing fuel for later, or am I burning the furniture to keep the house warm? That's the fundamental choice.
Okay.
And the master controllers, the two generals in charge of that decision, are insulin and glucagon.
Let's unpack that, because I think most people view insulin as just, the thing that lowers blood sugar, like a janitor that comes in and sweeps up the mess after you eat.
Well, that is the outcome, yes. But its function, its purpose, is to manage abundance. When you eat a meal, especially one with carbohydrates, you are flooding your system with energy, way more than you can use in that immediate moment.
But you can't burn it all at once.
You can't. So insulin is the signal that goes out and says, hey, everyone, we're rich. We just hit the lottery. Start burning your reserves. Start saving all this new stuff. It tells the liver, the muscles, and the fat cells to open up their doors and just hoard resources.
It's the hormone of we have more than enough.
Exactly. And then glucagon is the complete flip side of that coin.
The scarcity hormone.
Precisely. Glucagon is the break glass in case of emergency signal. When you haven't eaten for a while or your blood sugar starts to drop, glucagon shows up and tells the body, okay, team, unlocking the vaults. We need that stored energy back in the blood right now.
So it's this constant tug of war. They're always balancing each other out. But before we get into the nitty-gritty of the molecules, and we are definitely going to get into the chemistry, let's look at where this is all happening. The control room. The pancreas.
The pancreas is, it's an interesting one because it's really two organs in one wrapper.
Yeah.
And I think that confuses people sometimes.
Yeah, I saw that distinction in the anatomy section of the notes. You've got the digestive part and the hormonal part, and they're not really the same thing.
Not at all. The vast majority of the pancreas, like the bulk of the tissue you'd see if you held one, is made of these things called shini. Their job is to secrete digestive juices, enzymes like trypsin and chymotrypsin.
Into the gut.
Into the duodenum, yeah, to help break down your food. That's the exocrine pancreas. That's the digestion story. But floating inside this sea of digestive tissue are these tiny, distinct little islands.
The islets of Langerhans.
The islets of Langerhans.
Which honestly sounds like a location from a fantasy novel. We must journey to the islets of Langerhans.
It does sound majestic, doesn't it? And in a human pancreas, you've got about 1 to 2 million of these islets. But they are tiny. Each one is only about, 0.3 millimeters in diameter?
That's minuscule. So even with millions of them, they're not a huge part of the organ's mass.
Nope. They only make up a tiny fraction of the total weight of the pancreas.
But despite being small, the notes say they're incredibly organized. It mentions they're built around small capillaries.
And that's a crucial detail. These islets are highly vascularized. They're wrapped in a dense network of tiny blood vessels, and you have to ask, why?
So they can check the blood and send out their hormones.
Instantly. They need to sense the composition of the blood second by second, and they need to be able to dump their hormones directly into the bloodstream to send that signal out to the whole body. They are the first responders to what's in your blood.
And this is where our cast of characters lives, the cells that make the magic happen.
This is their home. So within these little islets, you have a few different specialized cell types. The absolute stars of the show, making up about 60% of the cells, are the beta cells.
And the beta cells are the insulin factories.
They are. They secrete insulin and another hormone called amylin, which we can touch on later. Then, making up about 25% of the cells, you have the alpha cells.
The ones that make glucagon.
Yep, the ones that secrete glucagon.
So the antagonists, in a way, are living right next door to the protagonists. It's like a sitcom setup.
Closely packed neighbors. And they're definitely not ignoring each other. Then you have the delta cells, that's about 10%. They secrete a hormone called somatostatin. And finally, a very small number of PP cells that secrete pancreatic polypeptide, though its function is a bit more obscure, so we probably won't dwell on it too much.
What I found really cool about this whole neighborhood in the islets is that they aren't just sitting next to each other, they're talking to each other. They're constantly communicating.
It's a very tight-knit local regulatory system. We call it intercellular communication. And it's fascinating. For instance, insulin actually inhibits glucagon.
So when the beta cells are pumping out insulin,
They're literally shouting at the alpha cells next door to shut up. They're saying, "We have plenty of energy. Don't you dare release any of our stored fuel."
that makes so much sense. You don't want to be pressing the accelerator and the brake at the same exact time.
You just spin your wheels.
Yeah.
And it goes further. Amylin, which comes from the beta cells too, actually inhibits insulin secretion. It's a bit of a negative feedback on itself. And somatostatin from the delta cells inhibits both insulin and glucagon.
So somatostatin is like the librarian of the group. The
Yeah.
shusher.
It calms everything down. It's a dampening signal. So you have this intricate local control system that fine-tunes the signal before the hormones even leave the pancreas. It ensures the message sent to the body is clear and not contradictory.
That is just, it's beautiful. Okay, so that's the anatomy. Now I want to zoom in on our protagonist, insulin. The source material goes into this little detective story about how insulin is actually made, and there was this specific detail about something called C-peptide that seemed incredibly important for doctors.
Yes, this is a fantastic piece of biochemistry. So insulin doesn't just pop into existence as the active hormone. It's synthesized in the beta cells, and it starts in the endoplasmic reticulum, the cell's factory floor, as a molecule called preproinsulin.
Preproinsulin sounds like a prototype.
It basically is. It's a long single chain of amino acids. Think of it as a rough draft of the final product. Then in the Golgi apparatus, it gets cleaved. It gets cut to form proinsulin.
Okay, so it's getting refined.
Right. And proinsulin is almost there. Imagine a long coiled chain. To make it active, a specific piece of that chain in the middle needs to be snipped out. That piece that gets cut out is called the connecting peptide, or C-peptide for short.
So you literally snip out the middle section, and the two ends that are left behind link up to form the actual insulin molecule.
Precisely. The final insulin molecule consists of an A chain and a B chain, and they're linked together by what are called disulfide bonds. That's the active hormone. But here is the clinical aha moment.
Okay.
When the beta cell packages this up for release, it packages the final insulin and the C-peptide together. So when it releases insulin into the blood, it also releases that C-peptide at the exact same time.
So they come out together.
In equal amounts. One molecule of insulin, one molecule of C-peptide. Always.
Okay. So why does that matter? Why do we care about this leftover scrap piece?
Because measuring insulin levels in a patient can be really tricky, especially if that patient is a diabetic who is taking insulin injections. Pharmaceutical insulin, the stuff you draw up in a syringe, is pure bioengineered insulin. It does not have the C-peptide. It's been purified away.
Oh, I see where this is going. This is clever.
It is, isn't it? So if a diabetic patient is taking insulin shots and a doctor wants to know, hey, is your pancreas still making any of its own insulin, or are these beta cells completely gone? They can't just measure the insulin levels in the blood.
Because they'd be measuring the drug they just injected. They wouldn't know which is which.
Exactly. But they can measure C-peptide.
Because if C-peptide is present in the blood, it could only have come from one place, the body.
Exactly. It is the definitive proof of natural endogenous insulin production. It's a brilliant way to distinguish type 1 diabetes, where C-peptide levels are usually very low or even zero because the factory is destroyed, from early stage type 2 diabetes, where C-peptide C-peptide levels might actually be normal or even high.
High? Why would they be high?
Because in type 2, the body is resistant, so the pancreas is working overtime, pumping out tons of its own insulin and therefore tons of C-peptide to try and get the job done.
That is such a cool clinical detail. It really shows how understanding the basic science, the synthesis, directly helps the diagnosis. Okay, so insulin is released. With its C-peptide sidekick, it enters the bloodstream. But it doesn't stay there for very long, does it?
No, not at all. It has a very short plasma half-life, only about 6 minutes.
6 minutes, that's it.
That's it. It circulates unbound in the plasma, which means it's freely available, and then it's cleared from the blood, mostly by the liver and the kidneys, using an enzyme called insulinase.
That seems incredibly fast. Why would the body build this really important molecule just to destroy it 6 minutes later? Feels inefficient.
It's all about control. This rapid clearance is absolutely crucial. You want the control system to be incredibly responsive or snappy. Think about steering a car. You turn the wheel, you want the car to respond instantly. If insulin hung around in your blood for hours, once you released it, you'd be committed. You'd keep lowering blood sugar long after you needed to. You'd overshoot the mark and end up with dangerously low blood sugar. You need to be able to turn the signal on and off very, very quickly to maintain that tight balance.
So it's a quick response team, comes in, does its job, and gets out. Okay, so let's follow it. It gets to its target. Let's talk about what happens when it gets there. The magic trick, as I called it in my notes. Insulin arrives at a cell, let's say a muscle cell. It knocks on the door. What happens next?
So this is where we get into the receptor mechanism, and the source material is very specific about this. The insulin receptor is what's known as an enzyme-linked receptor. It's a big protein that sits in the cell membrane, and it has 4 parts, 2 alpha subunits that stick out on the outside of the cell, and 2 beta subunits that penetrate all the way through the membrane into the cell's interior.
So the insulin molecule in the blood is going to grab onto those alpha subunits on the outside, like a key going into a lock.
That's the perfect analogy. And that binding event on the outside triggers a dramatic change on the inside. The beta subunits become what's called autophosphorylate.
Autophosphorylate. Okay, so they turn themselves on.
That's a great way to put it. They add a phosphate group to themselves. And this act of autophosphorylation turns on a very powerful enzyme that's part of the receptor itself. It's called tyrosine kinase.
Tyrosine kinase. That sounds like the ignition switch.
It absolutely is. Once that tyrosine kinase is active, it sets off a cascade, a chain reaction. It starts phosphorylating a whole group of other enzymes inside the cell, which are called insulin receptor substrates, or IRS for short.
So it's a domino effect.
A huge domino effect. And the result is dramatic and multifaceted. It's not just one thing happening. It's a whole series of dominoes falling all at once inside that cell.
This is the part that just blew my mind. The way the source material describes the end result. It's almost like cargo ships suddenly appearing at a port.
That's a really good way to visualize it. So inside the cell, just floating around in the cytoplasm, there are normally these little bubbles called vesicles, and they are packed full of glucose transporters.
Or doors.
The doors. Specifically, a type called GLUT4 transporters in muscle and fat cells. Normally, these doors are hidden away inside the cell. The cell membrane is essentially a solid wall. It's closed to glucose.
So the glucose in the blood is just banging on the windows, but it can't get in.
Correct. But seconds, I mean literally seconds after insulin binds to that receptor and starts the tyrosine kinase cascade, those vesicles get a signal. They rush to the surface of the cell, they fuse with the cell membrane, and suddenly the cell is studded with open doors.
Wow.
And glucose floods in. The glucose uptake by the cell increases markedly, sometimes 10 to 20 times the baseline rate, all within seconds of that first signal.
And what happens when the insulin goes away? Did the doors just stay open?
No, and this is just as elegant. As the insulin detaches from the receptor, the process reverses. Those GLUT4 transporters pop back off the membrane, they form a vesicle again, and they go back into storage inside the cell, just waiting for the next insulin signal.
It's incredibly dynamic. The cell is physically changing its surface structure in real time.
It is. It's remodeling itself based on the hormonal environment.
And it's not just glucose, is it? The membrane permeability changes for other things too.
That's right. The membrane also becomes more permeable to amino acids, to potassium ions, and to phosphate ions. And this is important because if you're going to be in storage and building mode, which is what insulin's telling the cell to do, you need all those raw materials inside, not just the fuel.
There are slower effects too, right? That's the immediate seconds to minutes effect.
Yes. Over hours or even days, insulin actually remodels the cell's internal machinery. It changes DNA and RNA transcription to produce more of the enzymes that are needed for storing glucose, fat, and protein. So it has these immediate, rapid effects on transport, and then these slower, long-term architectural effects on the cell's whole metabolic profile.
Incredible. Okay, so that's the mechanism. Now let's look at the different arenas, as the outline calls them, where this whole drama plays out. It breaks this down into carbohydrates, fats, and protein. Let's start with arena 1, carbs, and specifically muscle.
Muscle is a fascinating case of, like, Jekyll and Hyde when it comes to fuel use.
Right, I read that. A resting muscle and an active muscle are totally different animals.
Completely different. So most of the day, your resting muscle, like as you're sitting here right now, it's not using very much glucose.
Right.
Its membrane, as we just discussed, is actually pretty much impermeable to glucose unless insulin is present.
So what's it running on?
It's running on fat. Resting muscle relies heavily on fatty acids for its energy. That's its default baseline fuel. But there are two major exceptions. The first one is heavy exercise. When you start exercising hard, the muscle contraction itself, and this is completely independent of insulin, causes those GLUT4 transporters to move to the membrane.
So you don't need insulin to get sugar into a working muscle.
You don't. The physical work itself opens the doors. This is so evolutionarily smart, right? If you're running from a tiger, you can't afford to wait for your pancreas to sign a permission slip to let the fuel in.
The demand creates the supply.
Exactly. And this is a huge reason why exercise is so incredibly beneficial for people with diabetes. It lowers blood sugar physically without needing the hormonal system to work perfectly.
And the second exception is right after a meal.
Yep. You eat a meal, your insulin level spikes, and that high level of insulin forces glucose into your resting muscles. Now, if the muscle isn't working, it can't burn all that sugar right away, so what does it do with it?
It has to store it.
It stores it as glycogen. Muscle glycogen is basically a private savings account of glucose ready for anaerobic energy bursts later. It can store up to about 2 to 3% of its own weight as glycogen.
Okay, so that's the muscle. Now the liver. The source material calls the liver the glucose buffer. I like that term.
The liver is the great regulator of the system. It's the central banker. So after a meal, when there's a ton of glucose pouring into the blood from your gut, the liver steps up in a huge way. Insulin tells the liver to do 3 main things, and they're all about specific enzymatic switches.
Okay, what's the first one?
First, insulin tells the liver to stop breaking down its existing glycogen stores. It inactivates an enzyme called liver phosphorylase.
So rule 1 is stop selling what we already have in the warehouse.
Exactly. Close the warehouse doors. Second, it dramatically increases the activity of an enzyme called glucokinase.
Well.
And this is a really clever bit of biochemistry. Glucoganase's job is to phosphorylate glucose as soon as it enters the liver cell. It sticks a phosphate group onto it.
Why is that so important? Why add a phosphate?
Because the liver cell membrane is always open to glucose. Glucose can flow in and out freely, but phosphorylated glucose, it's trapped. It's chemically altered in a way that means it can't diffuse back out through the transporter.
So insulin effectively pushes the glucose in and then instantly locks the door behind it.
That is a perfect description. It's a brilliant trapping mechanism.
And the third thing?
The third thing is it turns on another enzyme, glycogen synthase, which takes all that trapped glucose and starts stringing it together into long chains of glycogen polymers. It starts building the inventory. The net result is that the liver sucks up about 60% of the glucose from a meal. It acts like a sponge and prevents your blood sugar from spiking to dangerously high levels.
That's a very, very smart sponge.
A very smart sponge. And then, and this is the beautiful part of the buffer system, between meals, when your insulin level drops, the whole process reverses. The trapper enzyme, glucokinase, turns off. The builder enzyme, glycogen synthase, turns off. And an enzyme called glucose phosphatase activates. This one's job is to rip that phosphate group back off the stored glucose.
Which unlocks the door.
It unlocks the door, allowing the glucose to flow back out of the liver and into the blood.
And why would it let it out?
To keep your brain alive. Which brings us to the most important exception in this whole story, the brain. The source text makes a really big point about the brain not playing by the same rules.
Yeah, it's not like muscle at all.
Not even close. Unlike muscle or fat, brain cells are permeable to glucose without insulin. They don't need the hormone to open the doors. For the brain, the doors are always wide open.
Which makes perfect sense because the brain uses glucose almost exclusively for fuel, right?
Right.
It can't really run on fat directly.
Exactly. It is a glucose hog, and because it relies so heavily and exclusively on glucose, it is incredibly vulnerable to low blood sugar. If your blood glucose level drops too low, the text says into the range of 20 to 50 milligrams per 100 milliliters, the brain starts to seriously malfunction.
And that's hypoglycemic shock.
That's hypoglycemic shock. You get irritability, confusion, then seizures, then coma. The entire regulatory system we're talking about, insulin shutting off, glucagon turning on, the liver releasing its stored glucose, is largely designed to protect the brain's constant, uninterrupted supply of fuel.
So the liver is banking all that sugar from a meal, largely so it can dispense it to the brain a few hours later.
That's the primary directive. You could say the muscle hoards glucose for itself, but the liver hoards glucose for the brain.
That is a fantastic distinction. Okay, let's shift gears and move to arena 2. Fat. This is where I think that abundance theme really hits home. The source material calls insulin a fat sparer.
Yes, and this is something people often overlook. We think of insulin as the sugar hormone, but its effect on fat metabolism is arguably just as powerful, if not more so. Insulin doesn't just help you store sugar, it vigorously, actively prevents you from burning fat.
How does it do that? What are the mechanisms there?
Well, it acts on the adipose tissue, the fat cells, in a couple of ways. First, it promotes fat synthesis. If the liver's glycogen tanks are full and it can't hold any more sugar,
The warehouse is packed.
the warehouse is packed to the rafters. Insulin tells the liver to take any excess glucose and split it into a molecule called acetyl-CoA.
Acetyl-CoA, that's a central metabolic building block.
It is. And in this state of abundance, it's used to synthesize fatty acids. These fatty acids then get packaged up into triglycerides inside particles called VLDL, very low-density lipoproteins, and they get shipped out from the liver to the fat cells for long-term storage. So yes, excess sugar literally becomes fat.
Okay, we all kind of know that part. But you said it prevents fat burning. That's the sparing part.
This is the most crucial mechanism for keeping fat locked away. Insulin powerfully inhibits an enzyme inside fat cells called hormone-sensitive lipase.
Hormone-sensitive lipase.
This is the master enzyme that breaks down stored triglycerides into free fatty acids so they can be released from the fat cell and used for energy. Insulin shuts this enzyme down hard. So as long as insulin is high, your fat cells are in lockdown. You cannot release your stored fat.
So if you're snacking all day and keeping your insulin levels consistently high, you are physically preventing your body from accessing its own fat stores for energy.
That is the fundamental physiology. You are in storage mode.
Yep.
You cannot be in storage mode and burn mode at the same time. The switch is thrown one way or the other. And on top of that, insulin also promotes glucose transport into the fat cells themselves, which provides the glycerol backbone needed to assemble even more triglycerides. It's a very potent fat-building and fat-guarding hormone.
Now, the outline has a section here titled, Life Without Insulin, the Lipid Disaster. That sounds ominous.
It is the metabolic reality of untreated type 1 diabetes. It's a chemical nightmare. Imagine you have zero insulin in your system. That powerful inhibition on hormone-sensitive lipase, it's gone. The enzyme goes completely wild.
So the fat cells just dump everything they have into the blood.
A massive, uncontrolled release of fatty acids into the blood. The plasma concentration of free fatty acids just skyrockets, and this has two major deadly consequences.
Okay.
First, the liver tries to mop up all this excess fat, and it converts a lot of it into phospholipids and cholesterol. This is why untreated diabetics often develop severe atherosclerosis, hardening of the arteries. Their blood is literally sludgy with lipids because the fat cells are just dumping their entire load.
And the second consequence, this is what leads to the diabetic coma, right?
Yes. This is ketosis and acidosis. The liver's mitochondria go into overdrive trying to oxidize all this fat. They're burning fat like crazy. But in doing so, they produce way, way more acetyl-CoA than the normal energy cycle, the Krebs cycle, can handle.
It's like flooding a car's engine with too much gas.
It's a perfect analogy. The engine is flooded, so that excess acetyl-CoA has to go somewhere. It gets shunted down an alternative pathway where it condenses to form acetoacetic acid,
Which is a ketone body.
that's the primary ketone body, and that, in turn, gets converted to beta-hydroxybutyric acid and acetone. These three molecules are the ketone bodies, and they flood the blood. Now, acetone is volatile. It evaporates easily. That's why patients in this state, in diabetic ketoacidosis, have acetone breath. It's a distinct, fruity smell like nail polish remover.
But it's the acid part that's the real killer.
That's the killer. Acetoacetic acid and beta-hydroxybutyric acid are strong acids. They overwhelm the body's buffering systems and cause the pH of the blood to plummet. Severe acidosis, a pH below 7, leads to coma and then death. It's not actually the high sugar that's the most immediate threat in type 1 diabetes. It's the lethal acid produced by burning fat in this chaotic, unregulated way.
That is just a stark picture of why this regulation is so critical.
Okay.
It keeps that incredibly dense energy source fat safely locked away until you actually need it. Okay, let's briefly touch on the third arena, protein. Because you often hear about bodybuilders using insulin, right?
We do, and there's a very solid physiological reason for it. Insulin is a highly anabolic hormone. It acts in very similar ways to growth hormone. In fact, our source material points out that they are synergistic. An animal that lacks either growth hormone or insulin will simply not grow properly.
So how does insulin help build protein? What's it doing?
It does a few things. First, it stimulates the transport of specific amino acids, the notes mention valine, leucine, isoleucine, tyrosine, into the cells. So just like it opens the door for glucose in muscle, it also opens the doors for the raw building blocks of protein.
So it provides the bricks for the wall.
It provides the bricks, and it also hires the construction crew. It increases the rate of mRNA translation, it turns on the ribosomes, which are the protein-making machines, and it even increases the rate of DNA transcription for certain genes, making more blueprints. It basically sends a system-wide signal to the cell, build stuff.
And at the same time, it stops demolition.
Exactly. It inhibits protein catabolism. It prevents the breakdown of existing proteins, especially in muscle.
And so, conversely, a lack of insulin would lead to protein wasting.
Severe protein wasting. If you don't have insulin, your body thinks it's starving, even if you're eating. So it starts breaking down its own muscles to release amino acids, which can then be used by the liver for energy. That's why untreated type 1 diabetics often look so emaciated. They are literally dissolving their own muscle tissue for fuel.
It's just a complete systemic breakdown.
Yeah.
So we've covered the three arenas. Now, I want to go back to the control room for a minute. How does the pancreas know how much insulin to send? We know glucose is the main trigger, but is it just a simple, linear relationship, more sugar, more insulin?
Not quite. It's a bit more sophisticated than that. It's what we call a biphasic response.
Biphasic, meaning two phases.
Two phases. Let's say you drink a big glass of orange juice. Your blood sugar starts to spike. Within 3 to 5 minutes, the insulin levels in your blood can increase tenfold.
That fast.
Incredibly fast. This is the phase 1 release. This is the pancreas dumping its pre-formed, pre-packaged insulin that was just sitting in granules in the beta cells waiting by the exit. It's the immediate emergency response.
Okay, so that's the initial splash to handle the first wave of sugar.
Right. But that ready-made stash runs out pretty quickly. The insulin levels might even dip back down a little bit. Then, starting at about 15 to 20 minutes, the secretion rate starts to rise again, and it can keep rising for hours. This is phase 2.
And what's happening there?
This is the factory turning on. The beta cells are actively synthesizing new insulin and activating the enzymatic machinery to release it. This second phase is sustained, and it continues as long as the blood glucose remains high.
And does it stop just as quickly when the glucose drops?
Almost immediately. It's a very, very tight feedback loop. Once your blood glucose drops back down to fasting levels, insulin secretion shuts off within minutes.
Are there other things that can trigger insulin besides sugar?
Yes, and this is an important part of the story. Amino acids. If you eat a high-protein meal, certain amino acids, especially arginine and lysine, will also stimulate insulin secretion.
Wait, why would they do that? If insulin's main job is storing sugar, why do we need it for a protein meal?
Remember the anabolic effect we just talked about. You need that insulin signal to drive those amino acids into the muscle cells so they can be used to build new protein. If you ate a big steak without an insulin response, those amino acids wouldn't get where they need to go nearly as efficiently.
Ah, I see.
However, the source material is clear that amino acids on their own only cause a small insulin spike. They work much more powerfully if there's also some background glucose present.
Got it. And what about the gut hormones? I've heard about these things called incretins.
This is a huge topic in modern diabetes medicine. Hormones like GLP-1, that's glucagon-like peptide 1, and GIP, are released by the cells in your intestines when you eat food. They travel through the blood to the pancreas and cause an anticipatory rise in insulin.
So it's a heads up. The insulin starts rising before the sugar from the meal even hits the bloodstream.
Exactly. It's the gut calling ahead to the pancreas and saying, "Get ready, big delivery incoming." This anticipatory release helps prevent the blood sugar from spiking too high right after a meal. It's a feed-forward mechanism. And many of the most effective modern diabetes drugs, like Ozempic or Wegovy, are actually mimics of these incretin hormones.
Fascinating. So we've spent a lot of time on the hero, or at least the main character, insulin. Let's finally bring in the other guy, the antagonist, glucagon.
The hyperglycemic hormone, secreted by those alpha cells in the islets, its job is essentially the perfect mirror image of insulin. Its primary function is to raise blood glucose concentration.
And it does this mainly by acting on the liver, right?
Yeah. Primarily, yes. Its biggest trick is a process called glycogenolysis, which is just a fancy word for breaking down the glycogen that's stored in the liver.
And the mechanism here, the source material describes it as an amplification cascade.
Yes, and it's a classic example of how a tiny, tiny amount of a hormone can have a massive physiological effect. It's incredible.
Walk me through it. It seemed really intense, like a huge chain reaction.
It is. So one molecule of glucagon binds to its receptor on a liver cell. That activates an enzyme called adenyl cyclase, which creates many molecules of something called AMP. Each of those KMP molecules then activates a protein kinase regulator, which in turn activates a protein kinase.
Okay, I get it. It's a domino effect where each domino is bigger than the last.
That's the perfect way to describe it. At each step, the signal gets louder and louder. The source text says that just one single microgram of glucagon is enough to raise blood glucose significantly within about 20 minutes. It's incredibly potent because of this amplification cascade.
And besides breaking down the stored glycogen, it can also get the liver to make new glucose, right?
Yes, that's its second major function. That's a process called gluconeogenesis. Glucagon encourages the liver to take up amino acids from the blood and convert their carbon skeletons into fresh glucose. This becomes really important during a long fast after you've already used up most of your liver glycogen stores.
Here's a paradox I saw in the notes, and I want you to explain it. We said that high amino acids stimulate insulin to help store them as protein. But the notes also say that high amino acids stimulate glucagon. Why on earth would they stimulate the hormone that does the opposite thing?
This is one of those brilliantly elegant evolutionary checks and balances. Imagine you eat a purely protein meal, a big steak, no potatoes, no bread.
Good.
The amino acids from that steak stimulate insulin secretion. That insulin drives those amino acids into your muscles, which is good, that's what you want. But that insulin also tells all your cells to start taking up glucose from the blood.
But you didn't need any glucose. There's no new glucose coming in.
Exactly. So if you only secreted insulin in response to that protein meal, your blood sugar would crash. You'd become hypoglycemic and your brain would starve.
Oh, wow.
So to prevent that, the amino acids also stimulate glucagon. The glucagon goes to the liver and says, hey, release a little bit of your stored glucose into the blood to offset the effect of that insulin. It perfectly buffers the brain against the potential hypoglycemia caused by eating protein alone.
That is just, it's incredible. It's perfectly balanced. It lets you use the protein without passing out.
It's an amazing piece of physiological design.
Before we move on to what happens when this all breaks, just a quick word on the mediator, somatostatin.
The product of the delta cells. Somatostatin has a very short half-life, only about 3 minutes. And its job, in a nutshell, is to tell everyone to slow down.
The dampener again.
The dampener. It depresses the secretion of both insulin and glucagon, and it also slows down stomach motility and absorption of nutrients from the gut.
What's the goal there? Why slow things down?
The theory is that it extends the period of time over which the nutrients from a meal are assimilated into the blood. It prevents you from absorbing and using up your food too fast. It smooths out the whole metabolic curve.
Okay, so that's the system when it's working perfectly. You eat, insulin rises, stores the fuel. You fast, glucagon rises, releases the fuel. Somatostatin keeps it all smooth. Now, let's break it. Let's talk about diabetes mellitus.
The word mellitus actually means sweet, which refers to the historic finding of sugar in the urine. And this is really a syndrome of impaired carbohydrate, fat, and protein metabolism. And as we all know, it comes in 2 main flavors.
Type 1 and type 2. Let's start with type 1. This used to be called insulin-dependent diabetes.
And juvenile diabetes because it typically has a very abrupt onset, often around age 14. In type 1, the beta cells in the pancreas are destroyed. It's usually caused by a viral infection or, more commonly, an autoimmune disorder where the body's own immune system attacks and kills its own beta cells. There's a hereditary susceptibility, but the trigger is often something in the environment.
So, to put it simply, the insulin factory is gone. It's been bombed out.
Zero production. or very, very little. The immediate consequence is that blood glucose rises dramatically. The source material says it can go from a normal of around 90 up to 300 to even 1,200 milligrams per 100 milliliters.
And at a certain point, the kidneys just can't hold all that sugar back.
That's right. There's a renal threshold. When your blood glucose goes above about 180, the kidneys can no longer reabsorb all of it from the filtrate, and it starts to spill over into the urine. This is called glycosuria.
And this leads to those classic textbook symptoms: constant thirst and peeing all the time.
Polyuria and polydipsia. And the mechanism is simple physics, osmosis. All that glucose in the urine acts like a sponge and it pulls water out with it, so you urinate massive amounts of water. This leads to severe dehydration, both in the blood vessels and inside the cells. And that dehydration triggers the thirst centers in the brain, causing intense thirst.
And we already talked about the other more deadly immediate threat for type 1, the fat metabolism part, the ketoacidosis.
Correct. That's the acute, life-threatening crisis. But then there's all the chronic long-term damage. Persistently high blood glucose is toxic. It damages blood vessels all over the body. It leads to heart attacks, strokes, kidney failure, which is nephropathy, blindness, which is retinopathy, and severe nerve damage, or neuropathy, which can lead to infections, gangrene, and amputation. It's a systemic poison at those concentrations.
Now, let's switch to type 2. This is the much more common form, isn't it?
Oh, by far. It accounts for 90 to 95% of all cases of diabetes, and it typically used to occur after age 30, although terrifyingly, we were seeing it in younger and younger people now.
And the mechanism here isn't a lack of insulin, at least not at first. The problem is insulin resistance.
That's the core issue. The number one risk factor is obesity, especially that deep visceral fat around the organs. What happens is that the target tissues, the muscle, the liver, the fat cells, they stop listening to the insulin signal. The receptors might get downregulated, or the signaling pathway inside the cell just gets gunked up and becomes less responsive.
So the pancreas has to shout louder to be heard.
Exactly. In the early stages of type 2 diabetes, you often see a condition called hyperinsulinemia. The pancreas is pumping out 2 or 3 times the normal amount of insulin just to keep blood sugar in the normal range. It's overcompensating for the resistance.
But eventually, it just can't keep up. It burns out.
It's a vicious cycle. The high insulin itself can contribute to more fat storage and even more resistance. Eventually, the beta cells become what's called exhausted. They can be structurally damaged by the overwork and by the toxic environment of high blood sugar and high fats. So in late-stage type 2, insulin production actually starts to drop, and those patients might end up needing insulin injections, just like a type 1 diabetic.
The treats approaches listed in the source material for type 2 are interesting because it doesn't always start with drugs. It starts with lifestyle.
Because insulin resistance, especially in the early stages, can often be reversed. Weight loss and exercise are powerful medicine. They can resensitize the cells to insulin. And exercise, as we mentioned earlier, opens those GLUT4 transporters in the muscle physically, bypassing the need for insulin altogether.
But there are drugs, too, for when that's not enough.
A whole arsenal of them now. Metformin is a common first-line drug that increases insulin sensitivity. There are drugs called sulfonylurias that basically squeeze the pancreas to force it to release more insulin. And then there are newer drugs like the SGLT2 inhibitors, which work on the kidney and block it from reabsorbing sugar, so you literally just pee out the excess glucose calories.
It's amazing how many different levers we've figured out how to pull in this system. Before we wrap up, I want to touch on the diagnosis section. There's something called the glucose tolerance test.
The GTT. This is the standard stress test for your whole glucose regulatory system. You have a person fast overnight, and then you give them a standardized load of 75 grams of glucose to drink, usually in a very sugary drink.
And then you just watch what their blood sugar does over the next couple hours.
Precisely. In a person with a normal system, blood sugar will spike, but insulin kicks in hard, and within 2 hours, it's back down to normal, usually below 140. But in a diabetic, it starts high, it spikes way higher, and it stays elevated for 4, 5, even 6 hours. It shows that the system is completely overwhelmed and can't clear the load.
One last condition the source mentions, which is the complete opposite of diabetes: insulinoma.
This is rare, but incredibly dramatic. It's an adenoma, a tumor of the islet cells that produces massive amounts of insulin, completely unregulated by blood sugar.
So it's a permanent abundance signal, even when you're starving.
Right. And the result is the blood sugar crashes to dangerously low levels. The patient goes into hyperglycemic shock. They get tremors, hallucinations, extreme nervousness, and eventually If untreated, a coma.
And it's a very different kind of coma from a diabetic coma.
Very different. In a diabetic coma, you have the acetone breath and the deep, rapid breathing, what's called Kussmaul breathing, because the body is trying to blow off acid. In hypoglycemic shock or insulin shock, the person is often sweating profusely, they're nervous, and then they just shut down because there's literally no fuel getting to the brain.
And the treatment is ridiculously simple.
Immediate glucose. An IV of glucose or a glucagon injection will wake them up almost instantly.
It's really just a story of balance, isn't it? As we close out here, I'm just struck by how incredibly resilient this system is, but also how fragile it can be.
It is so elegant. That switch between insulin and glucagon is what allows us to survive periods of feast and famine. It's designed to protect our brain at all costs, but our modern life, with constant abundance, endless calories available 24/7, it basically jams the switch in the on position.
We're living in a state of permanent feast, and our physiology was never designed for that.
Never. We're exhausting the controller. The beta cells are being asked to run a marathon every single day with no rest.
And that's the road to type 2.
That is the road. If there's one single takeaway from this whole deep dive, it's to respect your pancreas. Give it a break. Let the scarcity hormone, glucagon, have a turn at the wheel once in a while.
Let the tank get a little bit empty before you fill it up again.
That's all it's asking.
Well, this has been an absolutely fascinating look into the chemistry that's happening in our own blood every single second. I will never look at a bagel or skipping lunch in quite the same way again.
Nor should you. It's happening in all of us right now.
Thanks for listening to this deep dive. Stay curious, stay balanced, and we'll catch you on the next one.